Good afternoon, students. In the today's video, we'll discuss about the norm instruction. Okay. So the main intention of the norm instruction is to normalize the value, a fixed point value. We are using the norm instruction to normalize the fixed point value. We are using the norm instruction, and especially we are concentrating on the signed number which is stored in the accumulator. We are trying to normalize the signed number which is stored in the accumulator. So when we are trying to normalize the fixed point number, we are separating the number into the mantissa and the exponent format. Mantissa and the exponent format. So here we are trying to normalize the signed number which is stored in the accumulator is now. So what is the meaning of that? So here, in order to give the explanation, I'm not considering the 32-bit number of our accumulator. I'm just taking some bits of the accumulator. Okay, now so don't think that it is a 32-bit. Actually, the accumulator register is a 32-bit register, but I'm not considering the 32-bit content for the explanation. I'm just taking the 4 bits to represent the value. Okay. So, but in the during the explanation of what is that status registers, we have seen one thing called as a sign extended mode bit. We have seen one thing called as a sign extended mode bit. Means there are the sign extended mode bit intention is it is indicating that there are some bits which are there as a part of the accumulator or as a part of one of the result of an operation is indicating, means some of the bits are indicating the sign of the number. So what I mean to say that in the last class we have seen one thing called as a -1. Okay, now let us suppose I would like to represent the -1. If you want to represent the -1, first of all you are supposed to write that one in the binary format. I'm just taking the 4-bit number. Same thing is applicable to the 32-bit number also. Okay, now so I'm just taking the 0001. So for one equivalent means here I'm taking the -1, but first of all, if you want to represent the negative number in the binary format, first you should write the for the magnitude. For the magnitude, you should write the equivalent to binary format. After that, convert that one into the convert that value into the negative number by applying the 2's complement, as we know that one, by applying the 2's complement. 2's complement is nothing but 1's complement plus 1. So if you apply the 2's complement to this particular number, if you apply the 2's complement to this particular number, so if you want, you can write the 2's complement as a 1's complement plus 1, but I'm directly writing this one as a 2's complement. So the equivalent to 2's complement number for the 0001 is a 1. 0001 is a 1, 1, 1, 1. So in this 4 ones, these 4 ones are indicating the these 4 ones are indicating the -1. Okay, now so the negative number which is represented in the binary format is a 4 ones. -1 is represented using the 4 ones. But if you see this one, only one bit is the actual magnitude, and remaining 3 bits are indicating the sign of that particular magnitude. Remaining 3 bits are indicating the sign of that particular magnitude. Okay, now means this one is called as a sign extended mode of operation. So actual information is only 1 bit, but the rest of the 3 bits are indicating the sign of the number. If you take the same number in the 32-bit format, then total 31 bits are representing the sign of the number, and only the least significant bit is indicating the magnitude of that particular number. Okay, now only least significant bit is indicating the magnitude of that particular number. In order to avoid this particular sign extended mode and normalize that value into the one format, into a particular fixed number format in the mantissa and the exponent format, and also in order to avoid the sign extension mode in the accumulator, because in order to represent the -1, we are taking the 32-bit number. In that 32-bit number, we are having the 31 bits. 31 bits are indicating the 1, which are nothing but those ones are nothing but sign of that particular number. Those ones are nothing but sign of that particular number. Okay, now to reduce the sign extension mode of operation and to show the actual value, what we are doing is we are using the norm instruction. We are simply using the norm instruction. The norm instruction is the one which is representing the value, signed value stored in the accumulator in the normalized format. When you are trying to represent the number in the normalized format, we are having the normalized format, that is a fixed point number in the normalized format. The fixed point number is converted into the mantissa and the exponent value. The fixed point number is indicating the mantissa and the exponent value. Exponent value means exponent value is indicating that how many number of bits are representing the sign of that particular number. How many number of bits are representing the sign of that particular number. Okay, now so that is indicated by the exponent. That is indicated by the exponent. So in order to reduce the sign extension mode bit, what we are doing is we are using the norm instruction. What this particular norm instruction will do means, what this particular norm instruction will do is, it will perform the exclusive OR operation between the two bits. Okay, now what I mean to say that here you are having the accumulator. So accumulator is a 32-bit number now. So I'm just taking the 32-bit number. So accumulator is a 32-bit number. I'm not representing all the bits over here. I'm assuming it is a 30. What is that? Accumulator 31-bit, accumulator 30th bit, accumulator 29th bit, and this one is the accumulator 0th bit. It is the accumulator 0th bit. Okay now. So here 0th bit, as per our example, we took the -1 now. So 0th, this particular bit is indicating the magnitude, and rest of the bits means this is a 0 bit, and this is a first bit, and this is a second bit. Okay, now if I'm taking the one more cell over here to indicate that one, then you can get the clarity. Okay, now so it is a 0th bit. 0th bit is indicating the magnitude, and rest of the bits from the 1 to 31. 1 to 31, total 31 bits are representing the sign of the number. But in order to normalize this one, in order to normalize the sign extended mode bit into the normal format, what I'm doing is I'm using the norm instruction. What the norm instruction will do means, every time it will perform the exclusive OR operation between the 31 bit and the 30th bit of our accumulator. Exclusive OR operation between the 31 and 30th bit of the accumulator. If the result of that what is that exclusive OR operation between these two bits of the accumulator is 0, then the test control bit is equals to the 0. Okay, now when we will get the 0 when we will get the 0, let us suppose in our example 31 bit as well as the 30th bit, both are the ones only. 31 bit as well as the 30th bit, both are the ones only. Okay, wait a minute. So 31 bit and the 30th bit, these two are the ones only. So when you are performing the exclusive OR operation between the one between the even number of ones, means exclusive OR operation between the two bits, and if both bits are the even ones, even number of ones, then the output is 0 now. So when you are observing the output as a 0 between the exclusive OR operation between these two bits, then we can comment that these two bits are same. These two bits are same. Okay, that means these two bits are indicating the sign of the number. So to reduce one bit, what we are doing is we are shifting this number to the left side. We are shifting that number to the left side. So that is indicated by this one. Okay, now so accumulator is shifted to the left side, and result of that particular left shift operation will be stored into the accumulator, will be stored back into the accumulator itself. And we are having the auxiliary register now. So one of the auxiliary register, which is represented by the ARP, auxiliary register pointer, which get incremented to indicate that the shifting operation is done to the left side. Okay, now means these two bits are indicating the sign bits. These two bits are indicating the sign of the number. So we are performing the left shift operation, and in order to indicate that the two bits are representing the same two bits are representing the sign of that number, the auxiliary register is incremented by 1, which is holding the exponent value, which is holding the exponent value. Okay, so now if at all the accumulator, if at all the result of these two, means if the result of the what is that exclusive OR operation between the 31 and 30th bit, between the 31 and the 30th bit, if the exclusive OR operation between these two bits is 1, if it is 1, okay, now we are expecting for the 0, but if it is 1, then what we are saying that if this condition fails, if this particular equal condition fails, then we are having the else part. We are having the else part. If at all the these two bits are different, let us suppose this is a bit 1, this bit position is a 1, and this bit position is a 0, then what will happen? Exclusive OR operation between these two becomes a 1. Because if we are having the odd number of ones at the input of the XOR gate, that the output is a 1. Output is a 1. So when it is a 1, if the result of this operation is a 1, then 1 equals to 0, the condition failed. 1 is equals to 0, condition failed. That's why we are entering into the else part. In the else part, we are placing the test control bit as a 1. We are placing the test control bit as a 1. Okay, now, means when we are having the difference between the 31 and 30th bits of the accumulator, at that time we can say that the sign is, means the 30th bit is not indicating the sign of the number, or I can say that the 30th bit is not a part of the sign of that number, sign of that particular number. Okay, now, if both are equal, then the 30th bit as well as the 31 bit both are indicating the sign of that number. Sign of that number. Okay, now, if both are equal, then they are representing the sign of the number. Because of that, what will happen? The test control bit is cleared and accumulator content is left shifted. When it is performing, when we are performing the left shift operation, obviously the LSB is filled with the zeros. LSB filled with the zeros. Okay, so that is the importance of the norm instruction. Okay, now so the norm instruction main intention is to normalize the accumulator content, signed content available in the accumulator. We are using the norm instruction. How it is performing? First of all, it is checking whether the whenever you are using the norm instruction, it is checking for whether the accumulator content is 0 or not. If it is 0, test control bit equals to the 1. Okay, now in the initial stage itself. If it is not 0, if the result of the if the accumulator content is not 0, then we are having this particular condition. Okay, and one more thing is the norm instruction is performing the indirect addressing mode of operation, because we are taking the auxiliary register, one of the auxiliary register, to indicate the exponent value, multiply and the exponent value. So that exponent value is indicated by the auxiliary register, and in order to show that how the auxiliary register is getting changed, whether it is incrementing or whether it is not incrementing, all those things are indicated using the star, that is a star plus and the star minus and so on. Okay, now so here we are having this symbol now. So if you want to know that one, what exactly the meaning of this symbol, so I'm having the table from the textbook itself. Wait a minute, I'll show you that table. Okay, now once we see the table, then it is very clear for you. Yeah, if we are having the star symbol, then it is indicating that auxiliary register content is not changed. Star plus auxiliary register content is incremented by 1, minus auxiliary register content is decremented by 1, 0 plus, indicating that auxiliary register is incremented by 1 with the index value of INDX register, with the content of the INDX register, or I can say that with the step size of the INDX value. So 0 minus auxiliary register content is decremented by the content of the INDX. By this means INDX value is taken as a step size, whether it is a 2 or 3, whatever the content which you are having, that is loaded into the INDX. With how much step size you would like to increment the auxiliary register content, that step size should be loaded into the INDX register. And these auxiliary register and the INDX register are part of our ARAU block, auxiliary register and arithmetic unit block. And after that, we are having the BR0 plus, so incremented by the content of the INDX with the reverse carry propagation. We will see the reverse carry propagation, what exactly the reverse carry propagation. Okay, now so these symbols are especially used in indicating the indirect addressing mode of operation. Okay, now so if any one of these symbols are used as a part of the instruction, then one of the operation is performed on the accumulator, that is the auxiliary register. Okay, now auxiliary register. Okay, now let us come back to our explanation. So here we are having this one. Okay, so star plus, star minus, star 0 plus, and so on. Okay, so this is the norm instruction. So the norm instruction main intention is to normalize the signed number which is stored in the accumulator, Okay, now let's go for the explanation of the addressing modes. So the next concept is the addressing modes. Okay, so addressing modes which are supported by DSP processor are: the first one is the direct addressing mode, and next one is the indirect addressing mode, immediate addressing mode, dedicated register addressing mode, memory mapped register addressing mode, and the circular register addressing mode. Okay, now so direct addressing mode, first addressing mode is the direct addressing mode, second one is the indirect addressing mode, immediate addressing mode, dedicated register addressing mode, memory mapped register addressing mode, and the circular addressing mode. Let us see the explanation of each and every addressing mode. So as I told you that when you are taking the data memory is divided into the page format. And again I told you that means in the previous classes I told you that the data memory is divided into the pages, and it is dividing the data memory into the 512 pages. How many pages are there? Means total 512 pages are there. Okay, now total 512 pages are there. So here if you see this one, there are the 512 pages. The data memory is divided into the 512 pages, named from page 0 to page 511. So named from page 0 to page 511. Total how many pages are there? 512 data pages are there in the data memory. 512 data pages are in the there in the data memory. Okay, now so here the direct addressing mode of operation is nothing but as a part of the instruction we are specifying the address ma. As a part of the instruction we are specifying the address, and whenever you are performing the direct addressing mode of operation, that address is a indicated. That address is indicated. If you see this one, direct addressing mode, the instruction contains the lower 7 bits. Okay now, so here the data page pointer, we are having the data memory page pointer, or the DP, data pointer. So this particular data pointer is there as a part of the status register 0, and this particular data page pointer playing a major role in direct addressing mode of operation. When you are performing the direct addressing mode of operation, 9 bits are coming from the 9 bits are coming from the data pointer. So actually, in order to access the 64 kilobyte 64 kilowords of data memory, we have the 64 kilowords of data memory now. So in order to access the total 64 kilowords of data memory, we require the 16-bit combination. But when you are performing the direct addressing mode of operation, at that time 9 most significant bits are coming from the data page pointer, that is a data memory page pointer, which is a DP bits available in the status register 0. These 9 bits are concatenated with the we have the instruction. Instruction is nothing but it is a instruction is a when you are writing the instruction, we have the opcode na. In that particular 16-bit opcode, 7 bits are indicating the 7 LSB bits, least significant bits of the opcode are indicating the least 7 bits are indicating the one of the page location. 7 bits means how many combinations you can get? 128 combination. You will get the 128 combination. So what I mean to say that the 9 bits coming from the DP, that is the data memory page pointer, which is a part of the status register 0, are concatenated with the 7 bits of the instruction register. That too, the 7 LSB bits are concatenated with the DP. So total how many bits are there? It is a 16-bit number. If you see this one, it is a DP and the DMA, totally forming the 16-bit data memory address. When you are performing the direct addressing mode of operation, then the 16-bit address is formed by the DP and the DMA by concatenating these 2-bit combinations. But in this case, the DP is there now. So what is the size of the DP? Size of the DP is the 512. Means the DP content is used for to selecting one of the DP means 9 bits now. How many combinations will get? 512. In order to choose one of the page number, these 9 bits coming from the DP are used to choose one of the page number from page 0 to page 511. So means DP content is used to select one of the page number, and the DMA content is representing one of the memory location in a particular page. Okay now, so page is selected by this bit combination. And one of the memory location in that particular page. Let us suppose I am accessing the page 0. Then this bit combination is means the 9 bits. These 9 bits are filled with the zeros. So obviously page 0. In this page, which memory location you would like to access, that is indicated by the rest of the 7 bits. Because using the 7 bits we are getting the 128 combination. So each page size is a 128 word size. Size, or I can simply say that 128 memory locations are there. Each memory location is able to hold the 16-bit number word information. It is able to hold the 16-bit number. Are we clear? So we have the DP indicating the is used for selecting one of the page out of 512, and DMA is used for selecting one of the memory location in the selected page. So this is about your direct addressing mode of operation. So in the direct addressing mode of operation, DP is indicating the data memory page pointer, and 7 bits are coming from the instruction, that is the opcode of that particular instruction. 7 LSB bits are concatenated with the DP, and finally it is forming the 16-bit number. So using this particular 16-bit number, we are accessing the memory location, that is the data memory location. Okay. So if you want brief explanation, simply I can say that DP is used for selecting one of the page, and the rest of the 7 bits are used for selecting one of that particular memory location in a particular selected page. Okay. So, and if you want a more detailed explanation about the direct addressing mode of operation, when you are taking the opcode of a particular instruction, let us suppose I'm having one instruction over here. Okay. So in this instruction, 010H is indicating the memory location. It is indicating the memory location. Okay, so otherwise, other way of explanation is the opcode for this particular instruction. The opcode for this particular instruction, which is also called as a mission code. So this is a mission code for that particular add instruction along with the 010 and the 5. Okay, now this is a what is that opcode for, or I can say that the mission code for this particular instruction. So how the DSP processor will differentiate that? What kind of addressing mode the DSP processor is performing means a particular instruction is using what kind of addressing mode, whether it is a direct addressing mode or indirect addressing mode. That is differentiated by the DSP processor by concentrating on the mission code, that too on the 7th bit position of our mission code. 7th bit position of our mission code. If at all the 7th bit position of our mission code is a 0, if at all the 7th bit position of our mission code which is representing one of the opcode of a particular instruction is a 0, then we are informing to the DSP processor that try to perform the direct addressing mode of operation. Try to perform the direct addressing mode of operation. If at all this 7th bit position equals to the 1, then the DSP processor need to perform the indirect addressing mode of operation. So if the 7th bit position equals to 0, direct addressing mode of operation. If the 7th bit position equals to the 1, then the microprocessor need to perform, that is the DSP processor need to perform the indirect addressing mode of operation. Indirect addressing mode of operation. Okay. But in the exam, no need to explain this complete information. Okay. It is a depth analysis how the microprocessor, that is the DSP processor, will come to know that whether it need to perform the direct addressing mode or indirect addressing mode. So that is done by go through the mission code of a particular instruction. If the 7th bit position is a 0, then it is that is the DSP processor need to perform the direct addressing mode of operation. If the 7th bit position equals to 1, then the DSP processor need to perform the indirect addressing mode of operation. Okay. So let us go for the indirect addressing mode of operation. As I told you that the indirect addressing mode of operation is done by it is taken care by the ARAU block. We are having the ARAU block now, which is nothing but the auxiliary register and arithmetic unit block. Auxiliary register and arithmetic unit block. So in that block, we are having the 8 auxiliary registers along with the INDX register as well as the ARCR register, auxiliary register and compare register, auxiliary register and compare register. So those 3 states are useful in performing the indirect addressing mode of operation. When you would like to access a particular memory location using the indirect addressing mode of operation, that particular value should be stored. Means that particular memory location should be stored into one of the auxiliary registers. One of the auxiliary register. But we have the one thing called as a ARP. We have one thing called as a ARP bit combination, which is the auxiliary register pointer. Auxiliary register pointer. So it is a 3-bit field, and this using this particular 3-bit field, we are choosing one of the auxiliary register. We are choosing one of the auxiliary register. Okay. So this particular, when you are performing the indirect addressing mode, then first of all you should indicate what is the auxiliary register pointer. With the help of the auxiliary register pointer, we are showing that which auxiliary register we are using in the in performing the indirect addressing mode of operation. So based on this content, as I told you that when you are writing a new value into the ARP bit combination, then the old value will be written back into the ARP, or I can say that it is a shard of the ARP which is holding the previous value of the ARP, and this particular, when you are writing the new value into the ARP, in this case I am writing the new value into the ARP as a 2, then we are accessing the second auxiliary register, which is nothing but the AR2. So by using this particular AR2, we are informing to the ARAU that I would like to make use of the AR2 to perform the indirect addressing mode of operation. And the step size of the jump of indirect addressing mode of operation is decided by using the what we take in the combinations, that is a star and the star plus. Okay, now we have this one, right? Star. So here we are using this particular one to indicate that no need to perform the decrement or increment operation on the auxiliary register content. Star plus, increment the auxiliary register by 1. Star minus, decrement the auxiliary register by 1. Star 0 plus, indicating that increment the auxiliary register by INDX content. So the step size is the INDX content. Okay, now. So that is used as a part of the indirect addressing mode of operation. Okay, now. So indirect addressing mode of operation is done by the auxiliary register and arithmetic unit block. Auxiliary register and arithmetic unit block. I told you that the 7th bit is the one which is differentiating what kind of operation it is performed by the DSP processor, right? So if you want, you can see this one. We have that one. So here we have the instruction format. Actually, we are not discussing more detail about the instruction format diagram, which what reveals so much of information about a particular instruction. so much of information about a particular instruction, but we are not here to discuss the complete information. Okay, so means what is the use of each and every bit. Okay, what is the use of each and every bit in your opcode? So every bit is having some meaningful operation. Okay, but we are not considering all of them. So here, if you see this one, the seventh bit, we are interested in the seventh bit, right? If at all the seventh bit equals to the 1, as I told you that it is perform means the DSP processor need to perform the indirect addressing mode of operation. If you see this one, if this particular bit position equals to the 0, if this particular bit position is equals to 0, so we are using the naming convention as a I, capital I. So if this particular bit equals to 0, then we are performing the direct addressing mode of operation. If this particular bit equals to 1, then we are performing the indirect addressing mode of operation. Indirect addressing mode of operation. Okay. So this is your means the rest of the bits explanation is also there, which is not required for us. Okay, because as I told you that the user guide is the one which is describing being the complete information about your DSP processor. Okay, but we are not at the student level. We are not interested to study all those things. Okay, let us go to the another one. Wait a minute. So the next one is the immediate addressing mode. The next one is the immediate addressing mode. Okay, wait a minute. I don't know. It is not leaving. Okay, it's just start up. No problem. So next one is the immediate addressing mode. So there are two types of immediate addressing modes. Again, one is the long immediate addressing mode. Another one is the short immediate addressing mode. One is the long immediate addressing mode. Another one is the short immediate addressing mode. Wait a minute. Come on, man. What happened to this? Oh my God. Okay. Why? Yeah, it's working. No problem. So immediate addressing mode. There are two types of immediate addressing modes. One is a short immediate addressing mode. Another one is a long immediate addressing mode. Short immediate addressing mode. Another one is a long immediate addressing mode. If immediate addressing mode is nothing but some constant, that may be the means in 8086 microprocessor. If we take the 8086 microprocessor, immediate addressing mode is nothing but it may be the 8-bit constant or the 16-bit constant. 8-bit or the 16-bit constant, right? Means some constant value is there as a part of the source. Some constant value is there as a part of the source to perform a particular operation, means to copy a constant value into one of the register or one of the memory location, where in place of the source we are having the some constant value, that may be the 8-bit number or the 16-bit number. So here also the immediate addressing mode is nothing but we have the source which is a constant, so depending on the constant size, we may have the short immediate or the long immediate. So if the constant size is a 8-bit, 9-bit or the 13-bit constant, if the constant value size is a 8-bit, 9-bit or the 13-bit constant, then that kind of addressing mode we call it as a short immediate addressing mode. If the constant value is a 16-bit number, then that kind of addressing mode is called as a long immediate addressing mode. So some of the instructions which are participating in short immediate addressing mode are these, and the other kind of instructions which are participating in the long immediate addressing mode are these set of instructions are participating. Okay, so short immediate addressing mode and the long immediate addressing mode is nothing but short immediate addressing mode means if the constant value is the 8-bit or the 9-bit or the 13-bit number, then it is called as a short immediate addressing mode. If the immediate value is what we can say, it is a 16-bit number, it is called as a long immediate addressing mode. So if it is a short immediate addressing mode, then whatever the data which we are having, that is indicated as a part of the machine code, which is nothing but the opcode. Okay, now if you see this one, the mission code for this particular instruction add space 0ffh. So the mission code for this particular instruction is this one. Okay, so in this case, these bits are indicating the output of the addition operation, and these bits are indicating the short immediate value. Or I can say that it is an operand. Operand is nothing but the immediate value, one of the constant. But here the constant size is the 8-bit size. So that's why it is called as a short immediate addressing mode. That's why it is called as a short immediate addressing mode. Now let's go to the long immediate addressing mode. So under the long immediate addressing mode, again we are having the one operand instruction or the two operand instruction. Okay, means we may have the one 16-bit number or the two 16-bit numbers. We may have the one 16-bit number or the two 16-bit numbers. So example for the one 16-bit number is this one. If you see this one, here the long immediate addressing mode with no data memory address means no data memory access means here when you are performing the immediate addressing mode, obviously it is a constant. So that constant is a data. That data should be there as a part of the data memory. As a part of the data memory. Okay. You may use the data memory address or you may not use the data memory address. If you are not using the data memory address, you should represent the constant value using the pound sign. So this is a 16-bit constant value. And here we are writing the value directly. No need to access the data memory. No need to access the data memory. Without accessing the data memory, I'm writing the a 16-bit constant directly as a part of the instruction. As a part of the instruction. Okay. So this one is called as a single or no data memory access format. The next one is a dual data memory access. Dual data memory access means, so this is an example for dual data access. This is an example for dual data access. If you see this one, the first operand is a 16-bit number, one of the 16-bit constant, and the second operand is indicating the address of the operand, another 16-bit number. Second one is indicating that second bit combination, that is this 012H number is indicating the address. Okay, address of the data memory. Address of the data memory. If you see this one, in this particular mission code, 7th bit position is what, 0. In this particular bit code, 7th bit position is a 0. 0 means we should make use of the DP value. So now the DP value is concatenated with the remaining 7 bits of our opcode, and finally it is forming the 16-bit number to access the memory location. 16-bit number to access the memory location. Okay. So another data is a directly means one operand is one 16-bit number is coming from the memory, and another 16-bit number is represented as a part of the instruction itself. As a part of the instruction itself. Okay. So this is what we are having the long immediate addressing mode. Under that we have the two operands. One is the single operand, another one is the two operands. In single operand we have the 16-bit constant directly, but in this two operands we have one of the operand is a 16-bit direct information, and another one is a memory address information. Means from that memory we should read the 16-bit number and perform the required operation. Okay, perform the required operation. Are we clear? So the next case is a dedicated register addressing mode. So the dedicated register addressing mode looks like our long immediate addressing mode only, but in this case only the two registers are allowed to perform the addressing mode of operation. If you see this one, the dedicated register addressing mode operates like a long immediate addressing mode, except that the address comes from one of the two special purpose memory map registers in the CPU. So here the address is coming, address is indicated as a part of the instruction, right? Address is indicated as a part of the instruction. But in the dedicated register addressing mode, address should be taken from either the DMAR register or from the DBMR register. Either of these registers should be indicating the address of the so and so 16-bit number, so and so 16-bit number, right? So that is about the dedicated register addressing mode. Okay, so it is just like a long immediate addressing mode only, but the thing is the 16-bit operand should be indicated using one of the dedicated register, which is a block mode address register or the dynamic bit manipulation register. Dynamic bit manipulation register. We have the lots of explanation, but no need to write that one in the exam, and also at the student level. Don't know, in order to avoid the confusion, I'm not explaining that. But actually, the mission code is the one which is talking about, which is talking a lot about your about a particular instruction, how it should be get processed by the microprocessor. But we are not considering that one. So the next one is a memory map register addressing mode. Memory map register addressing mode means in order to access the during the explanation of the memory map registers concept in the third unit, that is architecture of the DSP processor, we have seen the memory mapped registers. Memory map register means totally 96 registers are mapped into the page 0. totally 96 registers are mapped into the page 0. Okay, now 96 registers are mapped into the page 0. Okay, so as I told you that some of the registers are the hardwired one which are there as a part of the architecture. Some of the register names are mapped to the memory location. So just like that, in the memory map register addressing mode, some of the registers are mapped into the some of the registers are mapped into the some of the registers are mapped into the excuse me, some of the registers are mapped into the memory. Okay, now so that too, you know one thing, wait a minute, let me take the diagram for that. So I'm having the DSP processor and I'm having the memory. So I'm assuming that this is my, wait a minute to give the clear information. Wait a minute. This is a DSP processor, another one is a memory. So this one is a DSP. Okay, DSP processor. Obviously, this one is a. I'm assuming that it is a. It is not the assumption. It is a mandatory actually. It is a page 0, right? So the whatever the 96 registers are there, CPU registers, those are mapped into the page 0. Those are mapped into the page 0 of your data memory. Okay, now so totally the data memory is divided into the 512 pages, which we have seen in the direct addressing mode of operation. Okay, now so 512 pages, but in those 512 pages, the some of this what is that CPU registers, which are nothing but the 96 CPU registers are there. Those 96 CPU registers are mapped into the page 0. Those 96 registers are mapped into the page 0. In order to access one of the memory location, memory location in the page 0, which is maybe allocated to one of the register, no need to use the 16-bit numbers, no need to use the 16-bit address, because the DP, whatever the DP we are having now, that is the data page pointer, data memory page pointer. So this particular data memory page pointer is filled with the zeros, and the remaining 7 bits coming from the instruction, they are indicating the one of the memory location in the page 0. One of the memory location in the page 0. What I mean to say that memory map registers are nothing but the registers which are mapped into the page 0. In order to access those registers, we may access those registers using the register name, or we may access those registers using the 7 bits of address. Okay, no. So no need to take the 16-bit address. No need to take the 16-bit address. Are we clear? So there is a memory map register addressing. Okay. So if you want the diagrammatical explanation, we are having this one, right? So the total 16-bit number actually, but the most significant 9 bits are filled with the 0, which is a data memory page pointer, which is a DP, and the rest of the 7 bits are indicating the one of the memory location in the page 0, and those memory locations are allocated for the the registers which are there in your DSP processor, right? So the next one is the circular register addressing mode. Circular addressing mode. So what is the main use of the DSP? The DSP main use is to process the signals, which we have seen that during the initial classes of our DSP, means that during the before starting the third unit, we have seen the explanation of the DSP, how exactly the analog signal is converted into the discrete format, and from there into the digital format. We have seen that one. Okay, now. So when you are taking the when you are trying to perform the say when you are trying to process the signals, we are supposed to use the some mathematical operations, some mathematical operations. Those are there in the DSP, digital signal processing. Actually, digital signal processor is a processor which is performing the digital signal processing methods. Digital signal processing methods. Okay, now. Few of this operations are the convolution, correlation, finite impulse response. Okay, now these are majorly used in means these using few of these methods, we are processing the signals which are observed. Okay, now what I mean to say that if you want, you can I told you that whatever the information which we are trying to give to the DSP processor, that is there in the analog format, but that should be converted into the digital format. For that, we are having the sampling theorem. After the output of the sampling theorem, we are having the discrete signal, and those discrete signals are converted into the digital format. Those discrete signals are converted into the digital format. Let me take the best example. Let us suppose I registered my thumb impression as an attendance in our college. Let us suppose I register my thumb impression as an attendance in our college, and every time means whenever I would like to give the attendance, I'm always giving my thumb impression. Okay, so whenever I'm giving the thumb impression, obviously we have the scanner to scan our what is that thumb. Okay, now to scan our thumb. Okay, now. So the scanned information should be matched with the already existed information. The scanned information should be matched with the already existed information. Okay, now. So the further the DSP processor would make done is it will compare the already stored information with the present information by sampling the analog information which I am giving the means right now whatever the information I am giving using my thumb, that should be sampled, and that sampled information should be compared with the already existed value. If both are matching at least to the 80%, means if the result of that matching is at least the 80%, then I can accept that particular as a person as a Balakrishna sir in the college. Okay, now. Otherwise I should oppose that particular what is that attendance, saying that the person is not recognized, means if the person is not recognized. So in order to compare the two signals, or in order to perform the operation between the two signals, one is a already existing signal and another one is a currently sampled signal, we are taking certain different types of arithmetic operations. One is a it is not the arithmetic operation, actually it is a kind of DSP signal processing operations now. Arithmetic means we have the addition, subtraction, multiplication, division, but it is not like that. But these are the special type of operations which are used in performing the means in comparing the signals, in comparing the two signals. Actually two signals, we have the convolution, correlation, and the finite impulse responses. Okay, now so when you would like to perform this kind of operation to for the comparison operation, we have a set of registers. We have a set of registers. One is a circular buffer register, and means two registers we need now. So one for the register one, circular buffer start register. SR is nothing but the start register, and this one is a circular buffer end register. So which is indicating the one signal information, and this one is a sampled information, or I can say that the second signal information to indicate the starting and the ending addresses. This one for indicate the first signal starting and the ending one, and this one for second signal starting and the ending one. And how many samples you would like to perform means how long you are supposed to repeat that operation. So that is indicated in the control register. We are not digging much into the how exactly these operations are performed, but we are simply knowing that what is the use of the circular register, or I can say that the circular addressing mode of operation. Okay, so in order to control the activities of this particular circular addressing mode, we are having the circular buffer control register. Okay, now so this is about your circular addressing mode. Circular addressing mode. Okay, now if you are having any queries regarding this one, let me know in the group. So with this, the addressing modes in our DSP processor and the instruction set of the DSP processor is over. If you are having any queries regarding this particular topic, like addressing modes as well as the instruction set in your DSP processor, let me know in the group. And with this, the third and fourth units in your microprocessor are over. Okay, now these two units are over. We left with the second unit. I'll start the second unit later. Okay, now so second unit is a completely individual topic. So the first half of the second unit is the individual, and the second half is also the different types of process like 802. We studied the 8086 in the first unit. In the second unit, second half, we will study about the 80286, 386, 486, and the Pentium 1, Pentium 2, and so on to the 4 and Pentium Pro processors. Different types of processors are there. We'll see that one in the second unit. If you're having any queries regarding the DSP processor, let me know in the group. So that's all for today's class. Okay, we'll continue with another syllabus in the next video. Okay, I may start the instrumentation or that what is it micro. I may continue with the microprocessor. I'll let you know in the next class. Okay.